talk is going to be on cost-free fairness in online correlation clustering, and Jason is going to present.
Hello, everyone. Good morning. My name is Jason Chatzitheodorou, and this is joint work with Eric Balkanski and Andreas Maggiori. So we'll be mainly concerned with fairness in algorithms. The main motivation for that is there's a growing need for fairness in decision making, and we are especially interested in applications where algorithms are impacting individuals. Therefore, we need them to be fair. Some applications like that are recidivism predictions, hiring processes, and credit risk assessment. These have been mostly studied so far in an offline setting where we know all the data in advance. But in reality, it seems that learning new data every day and having to adapt to that is a more challenging objective. So we focus on that. The problem that we are studying is correlation clustering. So we start with the offline version. We just take as an input a graph on n nodes, and we minimize the disagreements. Now the disagreements are defined as the number of edges within each cluster we create, which are missing, plus the number of edges between different clusters. So as you can see here, if we cluster this graph with these two clusters, we have 4 missing edges in the left cluster, and we also have an edge that goes between these two clusters. So we pay a cost of 5. On the other hand, if we were to cluster like this, with these 3 clusters, we only pay 2. So this is a much better solution in our objective. Now, since we are interested in the online of the version of the problem, our input model is that the nodes are arriving in online fashion, and on its iteration, when a node arrives, we are learning, we are finding out what their edges are with the previous nodes. And the main difference with the classic online setting where we make irrevocable decisions is that we allow recourse. So on a later iteration, we are allowed to change our clusters in the past. Of course, we don't want that to be a huge change, but this is something that has been studied in the past as a way to improve approximations, competitive ratio, etc., in multiple problems, not just clustering. A little bit more formally, recourse in our setting will be if we have a recourse R if for any instance and any node, this node changes the classes that it is in at most R times. So it is for every single node in our graph. And now it is important to know that why are we so interested in this is because in the standard online setting without recourse, there are very strong impossibility results. So there is nothing really to do in our problem. Now, since we mentioned that our nodes will be individuals, that's where the fairness constraint, our interest in fairness arises. So let's see the setting of fairness that we are considering. We assume that all our nodes are partitioned in L different colors. These will be the protected features in our setting, and for each one of those colors, we are given a ratio as input. These are the A1 to AL. And now, clustering, we would say that the clustering is fair if inside every cluster, the number of nodes that have a specific color are at most an AI fraction of this cluster. There's a small exception to that. We also allow clusters to be singletons, and we consider that fair as well. And this is the standard definition of fairness in clustering, which is closer to the idea of disparate impact. Again, we deviate a little bit from that in our problem. We define raw fairness, which only changes in this 1 plus rho factor there. It relaxes the classic definition a little bit. And the reason why we need that is because even in the offline setting, the papers that have considered this problem needed this relaxation in a crucial way. As an example of an application of correlation clustering that needs fairness, imagine that we have individuals that we need to, with different colors that we need to label. And label each and every one of them one by one has a very high cost. So instead of that, we group them up. And from each one of these classes we have created, we choose one, we label it, and we give that label to all the individuals in the clusters. Since now these labels will be used to make decisions about all these individuals in these clusters, we are interested in fairness, and we could maybe see that in this example there is a proportional representation of individuals maybe in its cluster, but if we were to do this instead, that wouldn't be the case. So that is somehow how fairness, why we're interested in fairness in this scenario. So, okay, as a whole, our motivating question is whether we can design online and fair correlation clustering algorithms. So we are combining both notions. And as a whole, how runtime would be is that first of all we would start by taking the fairness parameters as offline input. Then, in every iteration, as we see a new node arrive, we see its color. And we also see the edges with previous nodes that it has. And our output is on every iteration a raw fair clustering of the nodes up to t. And the recourse comes into the fact that the previous nodes up to t minus 1 can actually change clusters compared to the previous iterations. And our objectives are to achieve fairness in the definition that we saw before, so raw fairness. Recourse, exactly as we saw before, and competitive ratio. Now, our competitive ratio is considered with respect to the optimal zero fair solution, where zero fair means that rho is 0, so it's more fair. It's a little bit odd in our definition, but we consider a competitive ratio with respect to that, and we want that for every single iteration. Okay, let's see some previous results on this. The best known fair algorithm in the offline setting is a raw fair and constant approximate algorithm. It assuming that all the ratios and raw are constants greater than 0. In the online setting, the best algorithm we know is the constant competitive and logarithmic recourse of Cohen-Odad, which is asymptotically optimal due to the fact that we have these two results on impossibility. One is that we actually need recourse in order to have any meaningful ratio. And the other is that if we aim to have constant competitive algorithms, then we actually need logarithmic recourse. We need to have log n changes in clusters. And our main question is what we lose in competitive ratio and recourse if we actually want to add fairness to online correlation clustering. And our answer to that is that we give a constant competitive and logarithmic recourse algorithm as long as these parameters, these fairness parameters, are constant greater than 0. Now, comparing with the two results we mentioned, you can see that the best known fair is similarly raw fair and O1 approximate, while the best known online is constant competitive and log n recourse. Therefore, this somehow combines both results, which is the best we can hope for when combining both settings together. This is a more formal version of our theorem. It is not probably very useful, but it shows the exact dependency on rho and AI. Now, the way our algorithm works is it works as a pipeline. It has 3 main parts, which is agreement, make consistent, and fair, make fair. These are 3 subroutines that are used. And on every iteration, a new node arrives, we run these 3 things, and we output whatever is given by make fair. The way it works is that the first subroutine creates the clusters, and the next 2 subroutines only refine them by simply removing nodes and making them singletons. each one of those subroutines is responsible for a different one of our objectives. Agreement algorithm takes care of competitive ratio, make consistent of recourse, and make fair takes care of fairness. So let's see a little bit more about each one of those. The agreement algorithm is something we take as a black box from Cohen-Odad, and what it does is to try to find approximate clicks in our graph. It's an offline algorithm, and what it does is it mainly deletes edges between nodes that have very different neighbors. They call that a notion of agreement between nodes. And then for what remains, for the edges that remain, it just classes the connected components. This is a constant approximation, and we use that to get a first clustering of the graph. Then we need to make sure that we don't just run agreement on every single iteration. That would increase our recourse too much. So we have a way of delaying our changes in clustering. The way we do that is we look at every node for every node in our cluster that agreement gives us. We look at those that were singleton in the previous iteration, and we ask whether their degrees doubled since they were singleton due to agreement. This is too many moving parts maybe, but if this is true, if the degrees has not increased a lot, basically, we remove these nodes from the cluster and we just have them as singletons. Let's see an example of how this works. Imagine that we are looking at a situation like this at some iteration. Now, in this case, it is reasonable that agreement would cluster our instance like this. U would be by itself, so it would be a singleton in this iteration, and its degree would be 2. Now, in the next iteration, the black node could arrive. Agreement might decide to actually put them together, but now we take U out of this cluster because its degree has not increased enough. Then maybe this node arrives, and if this should happen, now the degree of U has increased enough that we keep it in the cluster. So this is mainly the way in which we delay this massive change in clusters in order to keep the recourse. Our last subroutine is make fair, which will take care of the fairness. And the way it works is to look at its cluster from make consistent and look at how much it violates fairness. If it violates fairness too much, so it's not even raw fair, we just split into singletons, the whole cluster. Otherwise, if it is raw fair but it is not raw over too fair, we simply copy what we did in the previous iteration. So if we split in the previous iteration, we do that, or if we kept the whole cluster, we keep it once again. In all other cases, if it is raw over too fair, we keep it. This introduces a multiplicative gap between splitting and unsplitting, and now it delays the creation of clusters. We do not create too many. Note that the important thing to note is that if we were to keep every single raw fair cluster that we are given by the previous subroutine, we could be incurring more and more recourse. So the image is something like this. If we have a very unfair cluster, see here the big difference in colors, we decide to split it. Otherwise, if it is a little bit unfair, let's say, we can't know for sure. We have to look at the previous iteration. While if it is a fair cluster, we simply output it. Now, with all of that, as an overview, we have studied correlation clustering, and the setting is online, input with recourse and with fairness constraints. What we give is a raw fair constant comparative and logarithmic recourse algorithm. The main implication is that there is no cause for fairness in our problem, and for future work, we could maybe apply this setting to other clustering objectives, maybe k-means, which is very popular, or facility location. Thank you very much.
We have time for one question. I'll ask. So you kind of have the best of both worlds for these two different results, one which was fair and one which was offline. I'm wondering how you specific quantitative guarantee compare with those. For example, like you have 1 over rho to the 5, I think.
Exactly.
how does that compare in, say, the offline setting? Are those sort of better results?
So yes, so in the offline setting, there is a, if I remember correctly, there is not the exponent, for instance. There is a 1 over rho or some dependency on polynomial rho and AI, but it's not maybe as big. But again, our analysis is not exactly tuned to capture that. Yes.
Okay. All right, let's thank Jason again.
Thank you very much.